Ohanian 5.69. This problem gives you a wall, a ball of mass m and radius r held against the wall by a string of length L. So we're given L, M, R, presumably no G, and we're asked to solve for the normal force. Well, we're asked to do the free body diagram first and solve for the normal force, and then what's the normal force in certain limits as L goes to infinity, and that's what the Ohanian asked, and I said also solve in the limit as L goes to 0. So let's start with the free body diagram. A free body diagram. Okay, so we have the sphere. We have a normal force pushing in this direction. That's the contact force from the wall acting on the ball. We have a force of gravity acting down, and we have a force of tension pulling up at some angle determined by where the length of the string. I'll call that theta for now. Okay, although you aren't given theta in the problem, remember. So I also need to define my coordinate system. So let me just go ahead and pick a conventional x to the right and y up. Okay. B, okay, now we've done free body diagram, we need to solve for a normal force. When you're asked to solve for a force, okay, you should think, well, Newton's laws. And so let's apply Newton's laws in the x direction. What are all the forces in the x direction? Well, T, the tension, has a component in the x direction given by T sine theta. Okay. And that's in my positive x direction. The normal force points in my negative x direction, minus n. And these have to sum to 0 because the ball's at rest. In my y direction, I just look at my free body diagram and I say, there's a component of tension upwards, which is T cosine theta. And there's gravity down. That's also 0. So I've got two equations, these two equations for two unknowns. The tension's unknown and the normal force is unknown, so I ought to be able to solve them, but I have a problem. I wrote everything in terms of theta, but you weren't given theta. Okay, you were given the length of the string and the radius of the ball. So now I have to use that information to get theta. So let me make another drawing over here showing you how I'm going to do that. So this is the wall, the ball, the attachment point. This string has a length L from here to there. Okay, the ball is hanging a height h. The center of the ball is a height h below that attachment point. And this is the angle theta that I wish I could use. Notice I can complete this as a right triangle if I extend the string towards the center of the ball. It has to do that, and then from the center of the ball to the wall. So I have a right triangle with this side being length h, this side being length r, and this side being length L plus r. Okay, so given the three sides of a triangle, I can certainly work out what theta is. That won't be a problem. So I can continue trying to solve it, knowing that I can, and whenever I want to, convert theta to the things that are given in the problem. Okay, and the easiest way to solve this problem, you can solve for the tension directly just by solving using this y equation. So the y equation will tell you T equals mg over cosine theta. Okay, then I can plug this into my x equation for the tension to eliminate tension from the system, and that will give me that the normal force is equal to T sine theta. Eliminating tension, I've got mg over cosine theta times sine theta, or the normal force equals mg tangent of theta. Okay, so I'd have the normal force if I can convert theta to the dimensions that are given me. So let's do that. Okay, how do I get theta out of my equation? Well, notice that tangent of theta will just be equal to r. Well, I can just do that directly. Tangent of theta is just the opposite side, r over h. Easy, okay? So the normal force then is equal to, actually, I better back up. We weren't given h in the problem. Okay, you notice up here I didn't include h as something that's given L. So I also need to work out what h is. Well, how am I going to do that? I'm given L and R. But h, okay, from Pythagorean's theorem, we know that L plus R quantity squared, this hypotenuse, has to be equal to R squared plus h squared. So I can solve that for h. Let's multiply this out. That's L squared plus 2RL plus R squared equals R squared plus h squared. These R squareds cancel. And so I've got h equals the square root of L times L plus 2R. So I've got the h that's in this expression for tangent theta, which I need for this. And now I can write down my answer for the normal force. The normal force equals mg. Tangent of theta is r. Well, that I'm given. So mgr divided by h. And h I've just solved for. The square root of L times L plus 2R. Done. I've got my expression for the normal force. And now I want to look in the two limits. L goes to infinity and 0 and see what I've got. Well, in the limit as L goes to infinity, it's pretty easy to see, well, if this gets infinite, then n goes to 0. And this should make some sense. If you're holding the string basically vertically, okay, then there's no reason for the ball to have much contact with the wall. So that should make sense to you. Okay. More interesting, I think, is what happens if L goes to 0. If L goes to 0, if you can imagine what's happening as you hold it to 0, at some point you're just trying to hold the ball directly against the wall, the string of 0 length. And that's going to be hard. And we can see it's hard by saying as L goes to 0, theta goes to 90 degrees. That's the easiest way to do this. And the tension, which is mg over cosine theta, okay, is going to be equal to, well, cosine theta goes to cosine theta goes to 0. Okay, so the tension blows up to infinity. Okay, so as the tension blows up to infinity, that means you're pulling the ball against the wall with infinite force, and the normal force counteracting that is also going to be infinite. Okay, so you're going to have a hard or impossible time to hold the ball at that angle. Okay, that's it.